Ew. All right. Good morning, folks. Hopefully, everyone had a good weekend. Hopefully, you had a good chance to get outside, enjoy the sunshine for a little bit, so you can help you deal with the gloomy weather that we have this morning. Okay, so let's go ahead then and let's pick up what we left off with on Friday, and we were talking about we were continuing our discussion of stoichiometry. And again, stoichiometry is the analysis, the examination of a chemical reaction in terms of the quantities involved in the chemical reaction. And so, again, that is how much reactants and products are involved in the chemical reaction. And so, essentially, stoichiometry looks at the amounts of reactants and products that are involved in a particular reaction. Okay? And so, we can examine the particular reaction in terms of moles, okay, the moles of each component of the reaction. We can talk about, we can examine a chemical reaction. We can in terms of the masses involved in the chemical reaction itself. And so that's where we left off with on Friday. I'd mentioned then that with certain reactions that involve gases, it's a little bit easier to measure out volumes involved in the chemical reaction because it's easier to deal with volumes of gases than it is masses. Okay, and so if the reaction involves all gases, and if the reaction is run at STP, and remember STP is standard temperature and pressure, we can do the analysis using liters of gases, the volume of the gases, because we know what the molar volume is. The molar volume of a gas 22 is 22.4 liters. That 1 mole of that gas will occupy 22.4 liters. And that's always true for any gas, regardless of the identity, as long as the gas is at STP. So we learned that back in chapter 10. We can apply that then to a chemical reaction that involves gases and be able to do the stoichiometry with the molar volume. And so what we did then was I showed you to make sure you take a look at that flow chart, that little flow chart that I gave you and that we went over on Friday, and be able to follow that. And hopefully you recall then that from that flow chart, we could not compare volumes directly. That is, in a chemical reaction, we couldn't find volumes directly from the chemical reaction. What we had to do is we had to convert the volumes into moles, and then once we had the moles, we convert it back into volume again. But the conversion involved 3 steps, and the 3 steps could be done independently. But I had shown you, and during the course of what we've talked about with stoichiometry, I've shown you that there's a simple process by which we can plug in all 3 conversion factors and do one long multiplication problem rather than do 3 separate calculations. Okay, and so that's what we're going to apply here as well. So I asked you on Friday to help us kind of go through this process. I asked you on Friday to come up with then the mole ratios. Now remember, for all these stoichiometric calculations, we will need the mole ratio. Okay? And to obtain the mole ratio, you need first and foremost a balanced chemical equation. So hopefully you got that written out for this one. I asked you to find the mole ratio that you would use to do this calculation here. And then I asked you to identify any other conversion factors that you may need. Okay. All right. So with that said, then let's take a look at this problem here and let's work this out. Okay. Let's work this out together. Okay. All right. So the first of all, make sure you get the balance equation. The balance equation, the reaction describes then nitrogen monoxide and oxygen in a combination reaction to form nitrogen dioxide. So let's go ahead and let's write down the equation first. So we need that. Okay. Let's write out the equation, and then we'll go from there. Okay. So nitrogen monoxide is NO. Okay. And we're going to react that with oxygen, diatomic oxygen, to produce first nitrogen dioxide. Okay. And so the balance equation is going to be 2, 1, 2. So those would be the coefficients for our balanced equation. Okay. The next step that I suggest you do is that I suggested that you write down, so remember, these are all conversions. So all these stoichiometric calculations involve conversions. And so with the conversion, any conversion, regardless of what type of conversion it is, 3 basic questions that you're going to answer. The first one is, what's the given amount? How much is mentioned in the problem? How much is given in the problem? And for which one of these components of the reaction? Then, second question then is, what are you solving for? Okay. And then the third question is, what are the conversion factors? So the first 2 questions, what I would suggest you do is after you get the balanced equation, write it in underneath the chemical equation itself. Okay, so here they tell us then that we have we start out with 34 liters of oxygen. Okay, so we have then 34 liters of oxygen. Okay, so that's what we're given. So in the problem it says then how many liters of nitrogen dioxide of gas are produced when 34 liters of oxygen reacts with an excess of nitrogen monoxide. Okay, I'm going to write this in now because it will be very relevant to our discussion in just a moment when we talk about excess and limiting reagent. Okay, so this is an excess, which means that they don't give us an actual amount. They just tell it to excess means that you have more than enough of this one, and that this is what you'll need. Okay, this is what's given to you. So we have nitrogen monoxide in excess. We have 34 liters. We only have 34 liters of oxygen, and so they're asking us the conversion then is how many liters of nitrogen dioxide is going to be produced. Okay, and so this is our conversion. So that's our conversion right there. That's what we're going to do. And how we're going to do it, we'll talk about that in just a moment. Okay, but one other key feature of this reaction that they tell us is that this reaction involves all gases. So I'm going to write in here. So that's a gas. Oxygen obviously is a gas, and nitrogen dioxide is a gas. So all these are gases, and the reaction is run at STP, standard temperature and pressure, which is 0 degrees Celsius for the standard temperature, and the standard pressure is 1 atmosphere. And we'll learn more about pressure here and what the atmospheric pressure means in chapter 13 when we get to it. But right now then, STP, you just need to recognize that STP represents these two conditions here. And furthermore, you need to recognize then that if we are going to use STP and all these are gases, we can use the molar volume as our conversion factor. Okay. All right, so with that said then, let's go ahead and start solving this problem. In order to solve this problem then, we have to be able to identify the conversion factors, okay? And so one conversion factor that we'll need, and this is the one I asked you to come up with, is the mole ratio, okay? All right, so what mole ratio will you use? Well, at this point, folks, hopefully you're not listing all the mole ratios. Now, if you want to do that as extra practice, if you want to do that because you still need to practice identifying the mole ratios, then go ahead and do so. But at this point then, what we'll need to know then is what is the mole ratio between this compound and this compound, because those are the two that are involved in this particular conversion. Okay, and so the conversion factor then, one of the conversion factors we're going to need then is the mole ratio, and I asked you to come up with that. Okay, and so the mole ratio then is going to be 1 mole, and the 1 because there's no number written in front of the oxygen then, it's implied to be 1. You have 1 mole of oxygen for every 2 moles of nitrogen dioxide. Okay, and then we can take the reciprocal. That means you can flip these two around and get the second mole ratio for this. Okay, and so which one of those two will we use? We'll see that in just a moment when we work out the reaction, work out the calculation itself. But so that's the first one. Hopefully, so if you need to, go ahead and pause the video, go get your paper from Friday, okay, and just make sure that you have this answer here. Okay, all right. So with that said then, the second conversion factor, what other conversion factors we need? We need the molar volume. Okay, why do we need the molar volume? Because they're asking us to find liters, the amount, the volume of this compound here, given this volume. So this is a volume to volume conversion of gases at STP. So the molar volume then, which is going to be 1 mole of the gas, and I'm just going to write it as 1 mole of the gas because we can use it for both, over 22.4 liters of the gas itself. So again, I'm going to write in gas, a generic word gas here, because then we'll plug in these two gases as we need it. Okay, so there it is. Those are the two conversion factors that we'll need. Okay, so let's go ahead then and let's work out this problem. Okay, so let's go ahead and work out this problem, and then let's get an answer. Okay. All right, so this is our conversion here. Okay, this is our conversion that we're doing. So we start out then with 34 liters of oxygen gas. So we're starting out with that. We are solving for then liters, and here it is on this side here, liters of nitrogen dioxide gas. So we're trying to find that number right there. We're trying to find what that number is right there. So we'll plug it in. Okay. All right, so we start out, we need a conversion factor that has liters of oxygen. Okay, so there it is, our molar volume. How will we plug it in? We'll plug it in as 1 mole. And again, the gas now, we'll put it in as oxygen, so we don't write the word gas. The gas that we're dealing with here first is oxygen over 22.4 liters of oxygen. Okay, why do we use this? Because that cancels out. Okay, all right, so that's the first conversion factor. What would the second conversion factor be? Well, the mole ratio then. We have moles of oxygen here. Okay, we've already used the molar volume for oxygen, so we can't use that again. So we will use the mole ratio. Okay, so how will we plug this in? Well, we plug it in so that the moles of oxygen will cancel out. So if we plug it in as 1/2, that doesn't work. We need to have the moles of oxygen in the denominator. So we'll plug it in then as 2 moles of NO2 over 1 mole of O2, which allows us to cancel that out. Okay. All right. So with that said, then the last conversion factor needs to get us from moles of NO2 to liters of NO2. Again, we'll plug in the molar volume. This time, though, we'll have 22.4 liters, and this time it'll be NO2 as the gas over 1 mole of NO2. When we do that, that cancels out. Okay. All right, so at this point then, hopefully you'll see then we're gonna double 34. Okay, so that means then we have then 68. So let me go ahead and erase this quickly. 68 liters of NO2. And that's our answer. Okay, so 34 times 2 times 32.4 divided by 22.4, and that's how we'll get our 68. Now, hopefully you recognize here also, folks, that actually the molar volume, actually cancels out as well. So really, actually, you're just doubling the initial volume right there. Okay? And so that's how we go about. That's how we go about solving, doing the stoichiometry on for gases. Okay? And so we saw at this point then, we have done 3 types of stoichiometric conversion. The first one involved moles to moles. The second one involved mass to mass. I'm sorry, 4 types. Okay? Mass to mass. The third type we did it a sample problem where we went from mass to number of particles, and you can go vice versa. And here now we have volume to volume. And so what I mentioned on Friday then is that we can do any type of stoichiometric calculation as long as we know then the conversion factors that we need, okay? And if we can identify the correct mole ratio. Okay. All right. Very good. So let's go ahead then and let's try a problem. Let me ask you to do number 11 here in your problem set. Take about 5 minutes to work out this problem here, and then we're going to go over this problem together. Okay, so take 5 minutes, work out this problem, and then I'll work it out with you. Okay. Okay, let's go ahead and let's work out this problem. Okay, let's take a look at what we have to do first. So first and foremost, we need a balanced equation, folks. So let's go ahead and hopefully you got that done. We need a balanced equation. Okay, so let's go ahead and write out our balanced equation first. Okay, and remember, you always want to start out with the balanced equation on all this. Okay, so we have that ammonia. They were told then that ammonia, NH3, okay, as a gas, reacts with oxygen as a gas to produce nitrogen monoxide as a gas and water vapor. Okay, so water as in its gaseous state. Okay. All right, so if you got all those formulas correct, then the balance equation then, if you got it right, is 4, 5, 4, 6. 4, 5, 4, 6 will get you balanced equation. So these are the coefficients here that we will use to balance. Okay. All right, next step. Let's go ahead and write down what we're given. Okay, we were told that we have 1.40 liters of oxygen. So if we have 1.40 liters of oxygen with an excess of ammonia, okay, so we have an excess of ammonia. The question then is how many liters, and the conversion then is how many liters of nitrogen monoxide will form. Okay, so this right here is the conversion we're going to do. We'll need the conversion factors to get that done. But what do we notice here? That's going to help us. We're told then that this reaction involves all gases at STP, right? So what are the conversion factors that we'll need to get this done? Well, let's go ahead and do this first. We need the mole ratio. We need the mole ratio between oxygen and nitrogen monoxide here. Okay, so the mole ratio is going to be then 5 moles of O2 over 4 moles of NO, or the reciprocal. Okay, so we're not going to use both. We're going to use one or the other. Okay, but make sure you keep in mind that whatever we're going to use has to have 5 moles of O2 or 4 moles of NO. Okay, so, or we can take the reciprocal. So that's our first conversion factor. The second conversion factor then, as you notice again, volumes, we're converting between volumes, and these are all gases at STP. So our second conversion factor then will be the molar volume, which is 1 mole. And again, I'm going to write this as generic gas because we're going to plug in the gases in just a moment. 1 mole of a gas over 22.4 liters of that same gas. Okay. All right. So the molar volume, remember, stays the same for any gas. The molar volume is not determined by the identity of the gas. It's just determined by the temperature and the pressure. Okay. All right, let's go ahead then and let's work this out. So the conversion then starts out, we start out with 1.4 liters of oxygen. And we're going to find then the conversion then is going to be to liters of nitrogen monoxide. Okay, so we're going to find out how much liters of nitrogen monoxide is equivalent to 1.40 liters of oxygen. Meaning that if we start out with 1.4 liters of oxygen, how many, what's the volume of nitrogen monoxide will form? Okay? All right, so first conversion factor that we're going to use then is going to be molar volume for oxygen, okay? It's going to be 1 mole over 22.4 liters. Hopefully you can recognize why we're using that, okay? Then the mole ratio is going to be 4 over 5, so it's going to be 4 moles of NO over 5 moles of O2. And again, hopefully you recognize you do that to cancel out moles of oxygen. And then finally, we need the molar volume for nitrogen monoxide, which is going to be 22.4 liters of NO over 1 mole of NO. Okay, and so with that said, then that cancels out. The unit of liters of oxygen cancel out. The moles of oxygen cancel out. The moles of nitrogen monoxide cancel out. The 22.4 liters cancels out. Okay, and so with that said, then we end up with liters of NO here and liters of NO here. We're going to go ahead and multiply 1.40 by 4/5, okay, which gives us then to 3 significant figures, 1.12. Okay, so make sure that you can do that, folks. Okay, so practice that. That was set B's homework. Okay, so practice that a little bit more if you need to. Now that we've done this, go ahead and go back and practice it and get this done. Okay. All right. Very good. So with that said, then let's go on then. And again, if you have any questions about the stoichiometry, folks, I'm available every day after school, 1:30 to 2:30 with my office hours, and so make sure you come by and get that extra help. Because we have to move on, and we have to take what we've learned about stoichiometry and apply it now to what's called limiting reagents. Okay? And then we'll talk about percent yield in just towards the end of this unit here, hopefully on Wednesday. Okay, so it looks like we may not finish up by the end of the week, so we may have to push the exam next week. But I'll let you know. Okay, so I'll let you know as we move forward how much time we'll need to invest into the remainder of this chapter. But what we need to do then is we're going to talk about what are called limiting reagents. We'll talk about percent yield towards the end of this section. But the reason why we need to talk about what a limiting reagent is, and we'll define what that is, why we need to talk about what percent yield is because when we run a chemical reaction or when we make anything, folks, okay, we need to know then how much we're going to make. If we're going to make cookies, for example, in the top example, we're going to make a salad or whatever it is, we want to be able to kind of get an idea of how much of that product we're going to get. Okay? And so with that said, understand this, that however much product we get will depend on how much of the ingredients we start out with. If we don't start out with a full complement of ingredients, we're not going to get the full amount of product that is expected in the recipe itself. Okay, so there's always going to be one of the ingredients that if you don't have enough of, that one ingredient will limit how much product we're going to get. So we refer to that limiting ingredient in chemistry then as the limiting reagent. Okay, a reagent is an ingredient. So that's how you want to think about this. Okay, and then with that said, then we want to be able to obtain what's called the percent yield. This percent yield then at the end of the process will allow us to determine then how well we did our work or how well the recipe, how good the recipe is in predicting how much product we're going to get. So these two numbers here, and so there are two calculations, there are two numbers that we will obtain, will allow us to determine how effectively we've done our work. Okay, so let's go ahead then, and let's talk about what this limiting reagent is. What's this idea of a limiting reagent? Okay, so in any chemical reaction, there's always going to be one of the reactants. And so when we talk about limiting reagent, a reagent, the term reagent just simply is another word, it's a synonym for reactant. Okay, so the limiting reagent is the limiting reactant. And the limiting reactant is the one reactant that will run out first. Whichever runs out first will limit how much product we're going to get. It'll determine how much product we're going to get. So that's how we're going to define the limiting reagent. Okay, so it's the reactant that runs out first because you don't have enough of it. And when it runs out, nothing else is going to happen. Okay, and so that it determines then how much product we're going to get. Now, this idea of limiting reagents doesn't only apply to chemical reactions, folks. It doesn't. It applies to real life as well. Okay. So, for example, when you make anything, for example, you make s'mores. Okay. If you run out of marshmallows, the number of if you don't have enough marshmallows, that will determine then how much of a s'more you're going to get. But you do know to start out with, and I think most people, the way you make a normal s'more is that you take one marshmallow, a couple of chocolates, and a couple of crackers, okay, a couple of graham crackers. Okay? And so if you run out of marshmallows first, then you're not going to make any more s'mores. Now, I'm not any s'mores in the traditional sense. I guess you can continue on and put a piece of chocolate in between two graham crackers and eat that, but that's not your s'more. Okay, that's not your s'more. But we're not limited just to talk about s'mores, folks, but we can talk about what's called, we can talk about hot dogs here. And if you want to talk about conspiracy theories, folks, I have one huge conspiracy theory, and this is one of my pet peeves that I cannot understand why it cannot that the hot dog bun people and the hot dog making people can't get together and work this out. Okay, because think about this: when you're making a hot dog, you need a bun, right? The most essential part. You need one bun, you need one hot dog, and therefore you make your hot dog. Okay, you need one hot dog, one bun. Okay, the problem that I have here, folks, and I'll finish up with this, and I'll step off my soapbox once I'm done here, is that if you ever go out and you buy hot dog buns, and then you buy hot dogs, okay, this is what happens here, and that is when you go out and you buy it, okay, and you go buy it, you buy a pack of hot dogs, you get 6 buns, you get 6 buns. Okay, that's what you have. You get the grocery store. You go over to the deli section and you buy your hot dogs here, and in each package they have 8 hot dogs. Now, what I don't get here is this. Okay, how hard is it for these folks here to get together and say, hey, you know what? If you're gonna only package 6 buns inside the package, we'll just pack 6 buns here as well. Okay, then no leftover, because you can imagine this: if you have 6 hot dog buns and you have 8 hot dogs, okay, you can imagine then the maximum number of hot dogs that you're going to form then is just 6 at the end of the process. Okay, and so if you have 6 here, you use up all this. You're not going to have any. So you're not going to have any buns left over. Okay, but you will have 2 hot dogs left over. Okay, and so what do you have to do? You need to go out. You don't want to waste anything, so you go out and you buy another package of buns. Okay, you buy another package of buns. Okay, which has 6 buns. Okay, and this time though, you only have 2 hot dogs. Okay? And so with that said, then you're only going to make 2 hot dogs in this particular at this particular time. Okay, so which means then at the end of this process, you're going to have no hot dogs left over here, but you're going to have 4 buns left over here. And so what do? You run out, you buy another package of hot dog, and you can see where this goes. So you can see where this goes. And so this is an industry-wide conspiracy, I think, where if you don't want to waste, you're going to have to continually buy hot dog buns or hot dogs in order to make sure that you get it done. So both the hot dog bun people are happy and the hot dog packing people are happy because consumers are continually buying this. Anyway, that's my little spiel. That's my little conspiracy theory there for you. Okay, but in each case here, if you notice here, to start out here, the number of hot dogs that you make here, is dependent on the number of buns. As soon as the buns run out, even though you have more hot dogs here, the number of hot dogs here that runs out that we make here is dependent on the buns here. So this is your limiting reagent. And that's what we refer to as the limiting reagent, because when this runs out, this runs out. We don't make any more. Even though we have more of this, we have this left. Okay, so we call this the excess reagent. Okay, so for this very first one, okay, we have 2 hot dogs left over for our very first trial here. We have 2 hot dogs left over. So the hot dogs themselves are the excess reagent. However, when you go to the second one here, okay, go to the second one here, we have then 2 hot dogs. If you notice here, that determines how much product we get. So this now becomes the limiting reagent, even though in the first reaction it was the excess. In the second one here is the limiting because it runs out first. And the buns this time will be our excess reagent, okay? Because we will have 4 left over. So just because we're running the same reaction, does not mean that we will always have the same limiting reagent and excess reagent. And this is something you got to make sure you get into your head as we move forward, because the limiting reagent and the excess reagent is not only determined by the reaction itself here. It's determined by how much of each reactant we have to start out with, okay? And so what we'll do tomorrow is that we're going to continue this discussion, and we're going to apply this now to chemical reactions, but the idea is still the same. The idea behind which one runs out first is still the same. And so we're going to apply it to chemical reactions. We're going to use stoichiometry to find then the limiting reagent. And so make sure you understand, if at some point you feel like you don't understand it, work it back to what I've just discussed here in terms of hot dogs and hot dog buns, okay? Because it's the exact same concept that we use, but we just apply it to chemical reactions when we move on and we talk tomorrow and we talk about limiting reagents, okay? All right, so with that said then, folks, make sure you submit your work for today. Okay, I'm sorry I ran a little bit over, but I did want to end up with this discussion here, and we'll pick up with this discussion tomorrow, and then we'll do our first set of limiting reagent calculations as well, okay? All right, folks, so very good. I will see you folks tomorrow.